Good morning. I will give a rapid introduction of X-ray as a probe of matter, material, and process. I'm Luigi Paolasini from European Synchrotron Radiation Facility in Grenoble, France. These are the outline of my talk. I will give a brief introduction about how the X-ray was discovered and how we can go from X-ray tube and to synchrotron radiation with a few examples. And then I will describe how the larger facilities designed to produce this synchrotron radiation work. I will give a brief introduction about the electromagnetic wave and photons. And I will go into the detail of the main interaction between X-ray and matter, describing the elastic and inelastic scattering, absorption spectroscopy, and a few words about X-ray optical properties. I follow my presentation. Look, if you want to know more, I take most of my presentation from the book of Jan van As Nielsen and S. McMorrow, Element of Modern X-ray Scattering Physics. X-ray were discovered by Röntgen in 1895, when Röntgen discovered that a penetrating form of radiation is able to pass through the human body. They call X-rays, and X-rays are produced by a collision of accelerated electron with a metal target in the vacuum. Here there is a sketch, an example of the old machine used by Röntgen. And suddenly, this discovery bring the new application for the medical imaging, what we call absorption contrast, because X-rays are strongly penetrating radiation, able to cross the body and to be stopped by atom with a heavy element inside the material, like the bone or the ring. Today, thanks to the X-ray and the coherence of the X-ray, it's possible to produce a very detailed image by what we call phase contrast microtomography. Here is an example of the reconstruction of violin. This technique, using the coherence of the synchrotron radiation, is able to inspect in a very deeply detailed, down to the micrometer scale, very large object. This technique, for instance, is used in paleontology to investigate industrial manufacture and human organs. The presentation of Paul Taforeau, the responsible of beamline BM18, will shed light about the secret of this technique. Back with the time, 1912, Max von Laue discovered that this radiation indeed is an electromagnetic wave because manifests an undulatory behavior. In fact, the X-ray wavelengths are comparable with the interatomic distance and molecular bond. And put in a single crystal, the image of the interference pattern appear in the photographic paper. This is called white beam analysis using multi-wavelength X-ray beam. Today, thanks to the brilliance of the synchrotron radiation, it's possible to use this white beam X-ray diffraction in protein serial crystallography, recording a large amount of Laue picture to reconstruct very precisely the electron density distribution in protein by injecting microcrystal in a flux and registering very fastly the resulting X-ray diagram. In 1913, Bragg formulated the very celebrated law which determine by using a wavelength of X-rays the interatomic distance by recording the scattering angle, here indicated as theta, and this relation is at the basis of what we call X-ray crystallography to determine the structure and the symmetry in the material. Here is an example. Today, the diffraction can be used, for example, at high pressure and high temperature to investigate the complex phase diagram of material, like in this case, the phase diagram of sulfur taken at 17 gigapascal and a very high heating temperature. The talk of Andy Fitch will show much more about the powder diffraction technique applied at the synchrotron facilities. X-ray tube was until 1912, after the discovering of Röntgen, was used extensively, but today the same technique is used in hospital, in airport, in rotating anode to produce a very intense beam. Here I want to shed light that the X-ray spectrum emitted by collision of electron with a metal target have a continuous energy spectrum called Bremsstrahlung due to the electron colliding in the metal, and two spike, two very high resonance, K indicated as K alpha and K beta. These resonances are produced by the excitation of electron from the core hole, which leave a core, which leave a hole into the deep electronic shell, and this hole is filled by surrounding electron. These give rise to what we call core hole spectroscopy, because these are called, and these transitions are called the fluorescence transition. And this is the next pillar of the interaction of X-ray with matter, which produce a very large method of application. For example, today it's possible to use the nano imaging by X-ray fluorescence to determine the chemical analysis. In fact, these interactions are element selective, and thanks to the very good spatial resolution of X-rays produced at large facilities, it's possible to map the potential toxic element, for example, here at the cellular level. How the large-scale facility are built and how the synchrotron radiation is produced. The discovery of synchrotron radiation arose in 1947 at the General Electric, when the physicist accelerating the electron in a betatron, which is a circular ring in which the electrons are injected across a very strong magnetic field, they observe a very sharp and visible light emission, and this light was called synchrotron radiation. The synchrotron radiation is an electromagnetic radiation emitted when charged particles, for instance, in this case, the electron, are moving at ultra-relativistic energy and are forced to change direction under the action of a strong magnetic field. When I say ultra-relativistic, I mean that the energy of this electron, but in general, other charged particles can emit synchrotron radiation, this energy is bigger than the electron rest mass energy, which is equal to the well-known Einstein formula, mc squared, where m, in the case of the electron, is the mass of the electron. And for the electron, this energy, the electron rest mass energy, is equal to 0.511 mega electron volt. So to produce synchrotron radiation, we need to accelerate electron at the very large energy, bigger than the electron rest mass energy. We define gamma, which is an important parameter, which is the ratio of the effective energy of the electron with respect to the electron rest mass energy. Here is an interesting formula because most of the large facility accelerate the electron at the order of giga electron volt. For example, a ESRF is an electron ring in which the electron have an energy of 6 giga electron volt. Gamma is equal to close to 12,000. So the electron at ESRF travel at energy 12,000 bigger than the electron rest mass energy. This gamma has important consequence also about the radiation emission, which arise in the forward direction, and we will see that this radiation is contained in a very narrow cone, which is equal to the inverse of gamma. Synchrotron radiation, of course, is everywhere in astronomy because most of the radiation of our galaxy is composed by synchrotron radiation, in which charged particles moving at the speed of light, close to the speed of light, emit very sharp electromagnetic radiation. For instance, the synchrotron light was first discovered in a jet emitted by M87, and today we know that at the origin of the strong magnetic field of this emission is a black hole, a massive black hole discovered by Event Horizon Telescope. How the synchrotron radiation is emitted? The synchrotron radiation is emitted by what we call relativistic Doppler effect, in which the radiation emitted by charged particles when they change the trajectory due to the action of magnetic field appear shifted in frequency, and this is the Doppler effect, from an observer which sits in a laboratory frame with respect the reference frame of the electron which emit this radiation. Delta T prime is the time for the electron to go from the point A to point B. If the electron emit a flash of light in A and then a flash of light in B, the two pulses arise, propagate toward the observer, and the observer see these pulse, these two flash, very much more closer to with respect the delta T prime in which these pulses was emitted by the electron. And this by a geometrical expression, in the case of observer form an angle alpha with respect the trajectory of the electron, is the Doppler effect, so the timing compression is given by this formula, which can be approximated because in general alpha is a very narrow cone, a very narrow angle, and beta is the ratio between the speed of the electron with respect to the speed of light. By transforming beta by the Lorentz factor, we can obtain finally this relativistic Doppler effect expression, which rely the time compression observed at the observer position. We can see that when the angle is 0, we obtain the maximum Doppler effect. If the angle alpha is equal to 1 over gamma, the Doppler effect is reduced by a factor 1/2. So most of the radiation observed at the laboratory system is contained in a very narrow cone close to the 1 over gamma. This angle of emission, 1 over gamma, is called natural opening angle, and the observer experience a huge horizontal apparent acceleration when it is sit exactly in the tangent of the trajectory of the orbit of the electron. And then this radiation emitted is linearly polarized in the plane of the electron orbit. If we go out below this plane, the observer look at polarization which is no more linear, but elliptical. Just to give some number, if gamma, the energy of the electron, is close to 10,000, 1 over gamma is equal to 0.1 milliradiant, so 0.0057 degree. So for one electron at least, the emission and this radiation code is really very narrow. Today, the large facility are the two kind. We have synchrotrons in which the electrons circulate in a closer orbit, or free-electron laser in which the electron travel in a linear accelerator. Here is an example of the picture of one of the ESRF, European Synchronous Radiation Facility based in Grenoble, and the other is the XFEL in Hamburg, long with an accelerator long more than 3 kilometers. How we can accelerate the charged particle, in particular in this case the electron, by using the Lorentz force. The Lorentz force is composed by two terms. One is the electric field, and the other is the effect of magnetic field which bend the trajectory of the electron. We can accelerate the electron by apply a force proportional to the charge multiplied by the electric field of, if you prefer, a difference of potential applied like in old X-ray tube in vacuum to the electron, but using a simple difference of potential. Today, with the conventional technology, we cannot reach more than 10 megavolt per meter. Instead, using the second part of the Lorentz force, we can apply much bigger voltage to the electron to obtain its acceleration of the order of 300 megavolt per meter. And we'll see that indeed the best method to accelerate the electron in an accelerator is to use this second part inside the radio frequency waveguide. Before to show that, here I wrote the equation of motion for one electron submitted by the Lorentz force as a function of time. We can see that the speed of the electron reach the speed of light in a very short time. Instead, gamma, which is its energy, is a linear dependence, and we take time to increase the energy of the electron. The dynamical electromagnetic field acceleration works by exciting with this second part of the Lorentz force a waveguide. But inside the waveguide is excited with a time-varying transverse magnetic field, what we call transverse magnetic 010 mode, in which the magnetic field is perpendicular and the electric field is into the direction of the electron motion. We synchronize the different elements of these cavities in order that the electron experience the electric field in the same direction of its motion, otherwise the electron will go back. And so the section of the LINAC, linear accelerator, are constituted by different parts with different lengths, and when the electron enter inside this cavity, it receives a synchronized electromagnetic field with the electric field in the same direction of its velocity. So electron passes through the different cavities just in time to surf the longitudinal electric field in this waveguide. The synchrotron itself is a storage ring in which first the electron accelerated by a linear accelerator, by a LINAC, and then they enter inside a booster. Sometimes some synchrotron have directly the LINAC connected to the storage ring. In the booster, the electrons receive in some radio frequency section the force to increase its energy, and when the electron reach the target energy, they are stored in the lattice, in the storage ring, and then when the orbit is stable, different front end can be opened, and the different beamline can receive the radiation produced by magnetic element like the bending magnet, which is the element of curvature to obtain a circular ring, or undulator, which are special device, and we'll describe very soon what they are. And then the different beamline organized in a different way can take these very intense and brilliant beam. So the resulting X-ray radiation is brilliant, and we see very soon what this means: pulsed, polarized, and energy tunable. These properties are given mainly by the most intense device, the undulator, in which the electron passes through an array of magnet with the polarity inverted. Instead to have a circular bending, they have a sinusoidal trajectory inside this spatially periodic magnetic field. And these two array of magnet with the polarity inverted have a number of period defined by lambda u. Lambda u is the number of reversing magnetic field, or if you prefer, the sinusoid that the electron have inside this device. And the spectrum of this radiation is not continuous like a bending magnet, but have some harmonics. We call the fundamental harmonics the first harmonic of the undulator, lambda 1, and this is proportional to the periodicity of the magnet array, is inversely proportional to the square of gamma, and depend by a parameter kappa, which is called the deflection parameter, which can be changed by changing the gap between the two magnets. In fact, when the gap is lowered, the magnetic field experienced by the electron is strongest, and the sinusoid is more accentuated. So kappa increase in this case, and the wavelength, the fundamental wavelength, increase. So by closing the gap, we shift the energy of the radiation toward the high energy. So if you prefer, lambda increase. If we open the gap, the sinusoid is more flat, and then the lambda decrease, and so we produce higher energy, lower energy when kappa increase, higher energy when kappa decrease. Another properties of the undulator, which is very important, is that the opening angle is no more proportional to 1 over gamma, but is proportional to 1 over gamma square root of n, where n is the number of period. This means that for long undulator, and this is the case, for example, for the free electron laser, the opening angle is reduced according to that. And it's time to define the quality of the source, and this is valid for any kind of source emitting some form of radiation, including neutron, which is called brilliance or brightness. The brilliance is the the number of particles per second with respect to the beam divergence, the source size, and the quality factor concerning the spectrum of the emitted radiation. The beam divergence is associated to the transverse coherence, and the source size is connected to the size of the electron bunch. In fact, we don't accelerate a single electron inside the ring, but we accelerate a cloud of electrons. And so the source size depends from how big is our electron cloud which is put inside the storage ring. The two terms, the beam divergence and the source size, correspond to what we call emittance. So if the emittance decrease, this means if the beam divergence decrease or the electron packet is small, the brilliance become to be much bigger. And this is the case, for example, here I put some example of the sun, the nuclear reactor here in Grenoble, the Institute at the Institute Laue-Langevin. They are close to what the brilliance of a bulb of 60 watt, or if equivalent to a rotating anode. We can see that thanks to the narrow beam emitted by large facilities, in particular XFEL, which is a factor 10 times bigger the brilliance with respect to the conventional large accelerator synchrotron like the ESRF, many order of magnitude of brilliance can be gained by this machine. Now I want to describe what are the X-ray, in particular, what are the electromagnetic wave, just a little recall, and why sometimes we call electromagnetic wave, sometimes we call this photon. The electromagnetic wave spectrum range from the radio wave up to the gamma ray, and the X-rays have a wavelength of the order of 10 to minus 10 meter. 10 to minus 10 is a unit which is called angstrom, and the angstrom are the length unit used to define the interatomic distance and bonding in a molecule. The wavelength is proportional to the inverse of the wave vector, which describe the modulus of the wave vector. The wave vector describes the direction of propagation of the light. The energy is defined as the product of the Planck constant time the frequency. And the electromagnetic wave in general are described by the Maxwell equation, and the traveling electromagnetic wave are transverse propagating wave in which the electric field and magnetic field are orthogonal each other. Following what I described before, the electric field of the emitted electromagnetic wave at the synchrotron by the undulator or by bending magnet, when we look at the radiation tangent to the trajectory of the electron orbit, is linearly polarized, and the polarization is indicated by epsilon, which is a versor in the same direction of the electric field. The Maxwell equation defines the relation between the vector potential, which describe a transverse propagating plane wave, which have a space periodicity and a time periodicity. So I want to stress that the X-ray produced by undulator are polarized and linearly polarized with the electric field parallel in the same plane of the electron orbit. X-ray length scale produce diffraction because in a very small material like natural material like protein, DNA, or eventually also can be used to investigate the diffraction in man-made material. There is a relation which is very important, which relate the 1 angstrom, so 10 to minus 10 meter, or if you prefer 0.1 nanometer, with the energy of the X-rays, which are equal to 12.398 kilo electron volt. So when we speak about X-ray of 12 kilo electron volt, these X-rays have a wavelength of about 1 angstrom. So there is a relation which related the energy in kilo electron volt to the wavelength in angstrom. We call soft X-ray the X-ray which range from 100 electron volt up to 2.5 kilo electron volt are the X-rays which range from 2.5 kilo electron volt up to 1.2 mega electron volt, which correspond to 2 times the rest mass energy of the electron. Behind this energy, we are in the domain of the gamma rays. But as anticipated, we fill the synchrotron not with a single electron, but with the electron bunch, and there is the possibility to fill the electron inside the ring with a different distribution, a uniform distribution, and the radiation, or resulting radiation, is pulsed. Here is an example of the bunch length, the bunch time length. 20 picosecond is the interval between the different bunch of electron in the case of uniform filling. This corresponds, if you multiply by the speed of light, to a bunch of the order of 6 millimeter. But we can fill the electron bunch with a hybrid configuration in which one bunch is isolated with respect to the other, or eventually fill the electron ring with a few electron bunch. In such a way, we are able to modulate the pulsed radiation to perform video of chemical reaction or study dynamical phenomena in nature. I want to also to stress that this possibility in the X-ray free electron laser can reach pulse duration of the order of 5 femtoseconds, so we can investigate also the complex theory like a very fast phenomena in physics. When we deal with the interaction between X-ray and matter, as far as we consider the electron propagating, for example, in optical element and so on, we can use a classical description. But when we want to investigate the quantum scale object and what the X-ray do with the electron in matter, we need to use, we have some limit about our knowledge of the frequency of photons and the position itself, the particle localization, due to the Heisenberg uncertainty principle. The oscillation of and so the wavelength of the X-rays and the particular localization given by the envelope of this photon pulse have some limitations. So when we lose information about the particle localization, we can determine precisely the wavelength of photons. But when we want to know the position of the photon, we lose information about its wavelength. And here there is the Planck-Einstein equation for the energy, for the momentum, and when we study the quantum scale object, we need to consider the quantum description and the quantum behavior of the X-rays as a quantum particle. So in quantum mechanics, there is some assumption that the particle, for instance, in this case, the photon, are represented mathematically by a spatial wave function. And when we want to find the probability to find a particle in an infinitesimal volume dV, we need to take the modulus square of this spatial wave function. And so we can imagine two ideal, what I call operative assumption. The case of infinite plane wave, of course, I indicate here only the spatial part. The wave function which describes the infinite plane wave is this exponential EKZ, which can be decomposed in sinus and cosinus term, imaginary and real part. And so when we want to define the probability of find this particle per unit of volume, we need to just to take the complex conjugate multiplied by the spatial wave function, and we obtain 1. So this operative assumption of infinite plane wave means that we have 1 photon everywhere per unit of volume. The other operative assumption are the spherical wave. The spherical wave propagate by one origin, from one source point and are described by a spatial wave function which decrease as the inverse of the distance. And when we want to take the probability of find a particle in this spherical wave, we obtain that this is proportional to the inverse of the square of the distance. So the density of particle in this case of spherical wave decrease as a power as the inverse of the square of its radius. When we want to measure the flux of particle, we need to determine the number of particle per incident, particle incident normally to a unit area per second. And so you need just to take the particle density times the velocity, which are all the particles contained in this cylinder. This operative assumption is important to define one important term, which is called the total scattering cross-section, which is associated to the effective area viewed by scattering particle. The total cross-section is defined by the total number of particles scattered everywhere in the space in all the direction per second with respect to the incident flux of particle. And here I indicate two cases, a case of a mechanical classical collision of ball. We can see that the ball number 12 don't have any collision, but only those balls which collide with a sphere of radius A have a scattering. And so if we apply this expression, we can see that the total scattering cross-section in this case is just given by the number of particles per unit area per second, which multiply the cross-sectional area, which is equal to the surface of this ball, and we obtain sigma, which is equal to pi a square, where a is the radius of the ball. But in case of the quantum case, we need to apply the previous definition, operative definition, and we can obtain that the total cross-section is equal to 4 pi b square. B is called scattering length, which is an important parameter because it depends from which kind of interaction the X-ray has with the quantum object. The differential scattering cross-section is used when we want to measure the number of particles which collide, which are detected in some position in the space. In this case, the differential scattering cross-section is equal to the number of particles scattered in a solid angle with respect the incident flux. And applying the previous description, we see that the differential scattering cross-section is equal to b square. B square is as a unit in Barn. Barn is a very small number, 10 to minus 28 meters square. And the differential scattering cross-section is equal to the total scattering cross-section divided by 4 pi. B is called the scattering amplitude. It depends from which kind of interaction we are dealing. For example, in the case of neutrons, which are neutral particles and so don't see any charge, they interact only by nuclear interaction with the nuclei, producing what we call nuclear scattering. Neutron possess also a magnetic dipole moment and can interact with those electrons in magnetic atom which lie in unfilled electronic shell, producing the magnetic scattering, what we call dipole-dipole magnetic interaction. X-rays otherwise interact with all the electrons in the material, and so the power, the penetration power is less that the neutrons are more surface sensitive, and we can distinguish two kinds of interaction: the electromagnetic interaction, or, as we see, what we call core-Hall interaction, producing the resonant X-ray scattering. The X-ray matter interaction can be divided by two kinds of process. We have the absorption process, in which the photons are totally absorbed by material, or a scattering process in which the photons are just deviating from the straight direction. Both the process produce an attenuation of the beam, of the forward beam. In the absorption process, we can see, we'll see later, we have different kind of process because the photons create a hole, as anticipated at the beginning, in the deep level, in the core level, and this hole can be refilled by surrounding electron producing fluorescence, or other process can be possible, like the electron emission. All these kind of process are element sensitive, can be used for a chemical analysis and also to determine the peculiar electronic properties of the material. For the scattering process, we can distinguish elastic process, in which the incident photon don't lose any energy, or the inelastic process, in which some energy is given to the material, producing what we call the inelastic scattering. Inelastic because the emergent photon lose or can eventually, in some case, acquire energy from these collisions. Concerning the photon scattering, we can have the elastic coherent scattering, called Thomson scattering. The inelastic scattering, which is incoherent, is called Thomson, or resonance scattering, which can be elastic or inelastic. And let us see now more in detail which kind of process are these. The basic interaction and most important interaction between X-ray and electron in the material is called the Thomson scattering. The Thomson scattering works in this way. The electric field of the photon apply a Lorentz force on the electron, which start to oscillate, re-emitting spherical wave around. We can notice that here the red line represents the maxima of the transverse polarized light, the electric field apply a force, the Lorentz force in the electron, so the electron start to oscillate up and down. And we can see that the radiation term, the spherical wave which are emitted, are antiphase. The surface indicates the maximum of the radiation term, are antiphase with respect to the incident wave. And these have very important implication, as we will see later on. So when we want to measure the radiated field, the ratio between the radiated field and with respect to the incident electric field, this is proportional to one term, which is called Thomson scattering length, which is exactly our B of the previous formula, but now we call this R0, which is the classical electron radius, and is equal to 2.82 10⁻⁵ angstrom. Notice the sign minus. This sign minus is due to this antiphase emission of the radiated wave by the electron. There is another important factor, which is this angle between the trajectory of the incident X-ray with respect to the angle of the observer. In reality, this radiation term is not properly exact, because when the observer is a 90° with respect to the incident photon beam, the observer don't see any acceleration of the electron, and so don't see any kind of radiation. So there is a polarization term, and this polarization term implies that when we have a detector in horizontal plane with respect to the incident and the scattered wave is a 90°, when C is a 90°, no radiation is emitted. And this can be expressed by the product of the incident and the scattered polarization vector. And so the differential scattering cross-section for the Thomson scattering is given by this simple formula, R0 square modulus square of the product of the two incident and scattered polarization. This is important because at the synchrotron, because the X-ray are linearly polarized, when we want to do diffraction experiment, for example, it's better to use a vertical scattering plane, because in this case, the observer, or if you prefer, the detector, see all time the acceleration of the electron, with respect to the horizontal scattering plane, in which the diffraction is washed up when this angle theta, the Bragg angle, is a 90° with respect to the incident photon beam. In general, there is the interaction of the free electron with the X-ray is much more complicated, because for example, in the case of magnetic scattering, we need to consider many kind of rare radiation term, because the electron possesses a spin. And so in the case we want to detail more, want to investigate the magnetic interaction between X-ray and electron, we have to take into account different kind of radiation term. The first term is the Thomson scattering, the electric field excite the electron motion, which remit an electric dipole. This is called electric dipole interaction. But the oscillation of the electron moves the spin of the electron, and the spin of the electron can remit a magnetic field, what is called a magnetic quadrupole. And so these radiation terms are called electric dipole incident, magnetic quadrupole remitted. And we have also different kind of interaction between the incident magnetic field with the spin of the electron, which in turn move the electron, which remit an electric dipole, and so on and so on. All these terms exist, are measurable, but are extremely weak because concern the relativistic interaction, which is reduced by the rest energy of the electron. Coming back to the Thomson scattering, let me see what happens when we consider the interference between the emission of two electrons when they experience an electromagnetic, an X-ray beam. In this case, if the detector is very far from the source, from the two electrons, and we choose as the origin on the first electron, the second electron emit the radiation which have some phase shift, and this phase shift is indicated by this expression exponentially Q dot Rn, where Q is the difference between the incident and the scattered wave vector. Of course, we consider the detector is in the far field limit, so very far, in order to approximate all the spherical wave emitted by the individual electron as a plane wave. And so we can build the differential scattering cross-section for this process, which involve two single free electron. And this is given by this expression, which can be represented here in the first graphic. Let me suppose that the scattering wave vector, so K minus K prime, so the difference between the incident and scattering wave vector. In the case Q is perpendicular to the relative distance between the two electrons, we obtain the scattering intensity, which is proportional to the square of this term, flat, without any kind of modulation. Instead, when the Q vector is parallel to the distance between the two electrons, we can see that the detected intensity, the square of the scattering cross-section, have a sinusoidal periodicity, and the first maximum, the 2 pi divided by the Q is proportional, is equal to the distance between the two electrons. This is a very simple and needed experiment of diffraction, in which by measuring the scattering intensity, so the Q dependence with respect to the intensity of what we detect our given scattering angle, we can determine the orientation and the distance of the two electrons. Of course, if these electrons are freely to rotate, we repeat the experiment with a large number of photons, we need to take the orientational average of this phase factor associated to the second electron, which is equal to sinus QR divided by QR, and we obtain as a function of Q, so as a function of the scattering angle, this typical modulation. The first maxima correspond to the interatomic distance, of course, but we can see that at the larger angle, this dependence, this oscillation become more and more smooth. Now we can extrapolate this two electron model to an ensemble of the electrons which are contained in some volume, and we need then to sum the phase factor associated to all the electrons. We obtain the expression for a differential scattering cross-section for an electron charge distribution just by sum all the phase factor with respect to one given origin, which of course is arbitrarily chosen. Of course, in this case, we neglect the X-ray polarization, which is always present. In general, when we have an atom, we have orbitals, so we have some peculiar distribution of the electron density inside the material, and the form factor is just the integral of the electron distribution, in which now the sum is replaced by an integral, and here is we have plot two cases. The wave function which describe two atoms, an hydrogen and lithium atom. We can see that in the hydrogen, the distribution of the electron cloud is much bigger than in the lithium because the Coulomb attraction between nuclei and electron. And if we built the form factor, which is equivalent to the Fourier transform of the electron charge distribution, we can see that the form factor for hydrogen fall down much more rapidly with respect to the lithium. And this is in general, the atomic form factor fall down when the electron cloud distribution is large. If the electron cloud distribution is smaller, is containing a small volume, the form factor is much more smooth. Now, if we have a molecule, we need just to build up the molecular structure factor, which take into account the form factor for each individual atom and the relative form factor. If the Q vector, for example, is in the direction of the fluorine atom in position A and the oxygen atom, the carbon atom in position 0, chosen as the origin, we can build up the molecular structure factor. The carbon, of course, the factor R is equal to 0, so we don't have the exponential, the phase factor. For the 3 fluorine atom, the phase factor is the same, and we can see by geometry that the projection along the Q vector is equal to the interatomic distance divided by 3. And the isolated atom in A R is just the phase factor EQR, because R is the projection of the distance on the vector Q. So we can build up the molecular structure factor. The square of the molecular structure factor is exactly proportional to the intensity we can measure with a detector as a function of the scattering angle. And we can see in blue line that the first maximum corresponds to the inverse of the distance of the first neighbor, so in this case R. And if, again, we want to take an orientational average, we need to eliminate the exponential factor, taking the orientational average and replace it with the sinus QR divided by QR and obtain the red line. Just an observation that if we have a liquid in which the molecule is freely to move, we need to take the orientational average, and we can remark that the intensity fall down with respect to the case in which the molecule is fixed in the space. And this is the case, for example, if we put this CF4 molecule in a lattice, in a crystal, and the crystal, of course, crystal mean that we have a repetition of this molecule in the space, which repeat in the space. When we irradiate this crystal with the X-rays, we can obtain much strongest intensity with respect when the molecule are free to move like in the liquid. So just to summarize, for the diffraction, for the coherent elastic diffraction, or if you prefer the Thomson scattering, we have defined the atomic form factor. The atomic form factor take into account the electronic distribution and the size of the electron cloud for the individual atom. if we have a molecule, need to build the molecular structure factor by summing the different 4 factors for the individual atom which compose the molecule, time the relative exponential factor which give the interference term. If we have a crystal, we need just to sum all the molecules inside the crystal, so what we call lattice sum, and the unit cell structure factor, which is just the repetition, the single cell, which repeat three-dimensionally in the space. The second important interaction between X-ray and electron and the free electron is the inelastic scattering, called also Compton scattering. This scattering does not produce any interference effect. It's due to the inelastic collision between a photon with the electron. The photon loses energy, and so the wavelength of the photon increases. We have a redshift, and the electron acquires some kinetic energy. By writing the relativistic interaction of this collision before and after the collision, we obtain this expression for the energy shift or wavelength shift, which is proportional to the incident wavelength and depends from this value of angle in which the photon is emitted, the Compton, called the Compton angle. The H divided by MC square is called Compton scattering length, and is an important constant in nature, which on top of that is related to the fine structure constant, and is equal to 0.0243 angstrom, approximately, of course. And so the energy shift is given by 1 plus the ratio between the Compton scattering length divided by lambda. We can see that the maximum energy shift, or if you prefer, the maximum red shift of the emitted photon, arises when psi is equal to 180 degrees. Is 0 when we are in the forward direction. So the Compton scattering is incoherent because the direction of emission of the electron is completely stochastic. The electron can go, and so the photon. And so don't produce any interference effect between the electron, like in the case of the Thomson scattering, but instead produce an important background, especially for light element, and when we want to put the detector in the backscattering position, so with the psi angle very big, like in this case represented in this picture, in which an incident photon beam of 20 kilo electron volt collide with a plastic foil which contain light element, and detector is in the backscattering position. We can see that the elastic scattering with respect to the Compton scattering is very weak, and the Compton scattering can produce a strong background, especially when we have a light element. Here is an example of the relation between the Compton scattering and the elastic scattering in helium, in neon, in argon, and krypton. We can see that Compton scattering in the case of light helium is much more important with respect to the heavy atom like the krypton, in which the Thomson scattering prevail. Thomson scattering intensity indeed approach Z square when Q equal to go to 0, in forward direction. The Compton scattering approach Z when Q tend to infinite, so a very large scattering angle. Today, at the synchrotron, is more popular to do diffraction with 2D detector, which have a very large input surface, very high spatial resolution, high dynamical range, high sensitivity, and can have a very fast readout. Putting the bidimensional detector at a different distance with respect to the sample open the possibility to study small angle scattering for a specialized, for liquid amorphous material or specialized synchrocrystal diffraction, or very close, for example, to measure the powder diffraction at the short working distance. In general, with the diffraction using bidimensional detector, we can measure also the diffuse scattering, and we can, by, for example, taking a rotation of the crystal around one peculiar axis and collecting all the data, and it's possible to reconstruct the reciprocal space. It's possible to determine eventually the quality of the sample. For example, if the crystal contains multiple phase, or if is present some static disorder, or there is some peculiar modulation, what we call structural diffuse scattering. But also it's possible to observe the thermal diffuse scattering, which is associated to the lattice vibration. The lattice vibration can be of the thermal origin, associated to the movement of the atom around the equilibrium position, but can be also correlated. So we can study the dynamics, for example, the sound propagation and the dispersion curve of what we call phonons, which can be acoustic or optics. And in general, the structure factor now contain a time-dependent term associated to the displacement of the atom around the equilibrium position. And so it's possible to study the dispersion curve of the material with appropriate diffractometer, which have a very high energy resolution of the order of milli-electron volt. The inelastic series scattering, so is based to the observations, to the determination of how much the incident photon lose energy as a function of the diffraction angle, as a function of Q. We can remark that the scattering triangle now is not equilateral, but have K different from KF. The reduction of KF indicate how much energy is given to the system to excite, for example, a peculiar vibration mode. Studying the phonon is important, for example, to study the sound velocity and elasticity in the material under different kind of conditions. For example, high pressure and high temperature. It's important for superconductor to determine which kind of optimum mode coupled with superconducting electron in order to produce the well-known properties of superconductivity. It's important to determine the thermal conductivity or the precursive precursive sign of some phase instability arising in the material. So the last part concerns the absorption and emission process. The absorption of the electromagnetic radiation change with the wavelength and depend from the characteristic properties of photon-matter interaction. The principle of absorption spectroscopy and emission spectroscopy is due to the photoelectric absorption. The energy of the X-ray are so strong that are able to completely ionize the atom, removing one electron from the core level, which leave an hole, which is subsequently filled by surrounding electron. We have the K edge when the L edge, L shell electron fill the hole, or the K beta when the M shell fill the hole. But we can have different kind of analysis by inspecting more complex interaction and process which involve a redistribution of the electron when these photoelectric absorption arise. So these concern the absorption and emission process, and the photoelectric absorption is very important in terms of cross-section because is dominant with respect to the coherent scattering associated to the Thomson scattering, or the incoherent scattering associated to the Compton scattering. We can see the Thomson scattering and the Compton scattering are sit well below the photon electric absorption cross-section in the energy of the X-rays. Above 2 times the rest energy mass of the electron, we are moving toward the gamma ray, in which we start to produce pair, and of course this domain is not in the case of X-rays. The basic model used for the Thomson scattering in the case of the absorption spectroscopies must be removed. A more elaborate model must be taken into account for the free electron. And in this case, we need to consider the fact that the atomic electron have some bonding with the nuclei, and we can associate this bonding with a spring which have a damping factor, and so this, in classical way, this system constitute an harmonic, a damped harmonic oscillator. The quantum case is which is an analog of this classical case, is when the electron is excited close to the Fermi energy level, and after some time relax and refill the hole previously lived. This lifetime, the core hole lifetime, is inversely proportional to 1 over gamma, and gamma is the analog of the classic case for a damping factor. So in this case, in a very good approximation, we can consider a classical description of this quantum process by calculating the amplitude and acceleration of this forced harmonic oscillator. This is the amplitude. We can calculate the acceleration as seen by an observer at the position R with some time delay, and building up this relation between the electric field radiated with respect to the incident electric field, as we have done for the Thomson scattering. Now we need to consider some frequency dependent term. And so the scattering amplitude now is no longer include only the Thomson scattering amplitude, but include 2 terms, a real term and an imaginary term, which are called anomalous term. These anomalous term give rise to a very important frequency-dependent refraction index. In particular, the imaginary term is associated to the absorption correction, is the dissipation term. So with this harmonic oscillation, we can build up a very approximate model in which the different oscillator can feel the absorption cross-section can be considered as a superposition of oscillator with the relative weight strength proportional to the absorption cross-section. In general, in quantum mechanics and in the theory, we consider the interaction Hamiltonian as a weak relativistic limit of the Dirac equation, and we use the quantization of the electromagnetic field with some annihilation operator for the photon beam. The linear term in the vector potential is associated to the emission absorption process. The quadratic term is associated to the scattering process. In general, it's much more complicated because if we want to include the relativistic magnetic interaction, we need to consider also the Zeeman term or the spin-orbit interaction term. For the absorption spectroscopy, most of the time, the first term is linear in the vector potential is considered. When we use the X-ray when we measure the attenuation which the X-ray have when they cross a material, this attenuation coefficient is called linear absorption coefficient, which is proportional to the atomic number density and absorption cross-section. We can see that when we tune the incident energy across the different absorption edge, we have one jump in the case of we call K edge, we have 3 jump in the case of the L edge, or we have 5 jump for the M edges. And this is due to the quantum rule associated to the degeneracy of the level. For example, the L level, the orbital angular momentum is equal to 1, so the degeneracy is 3. For the M edge, the orbital momentum is 2, so the degeneracy is 5. And so this jump corresponds exactly to this kind of transition. In general, we can use the scale factor for the energy and atomic number, and we can see that the absorption cross-section depends from the inverse of the cube of the energy, and is proportional to the power 4 in the atomic number. We can see different elements with in which I use this scale factor. The K edge follow more or less the same rules, as well the L edges and so on. When we have a gas, for example, here we tune the incident energy across the K edge of krypton, we can see that this jump is well respected. But when we put this krypton gas over a graphite surface in order to produce a 2D crystalline material, we can see that this jump is replaced by a more complex region. We call this region XANES, near edge structure, absorption near edge structure. And the other region, which is associated to this oscillation, which is called extended X-ray absorption fine structure, EXAFS, and all these kind of investigation close to the edge or far from the edge give rise to specialized spectroscopy in which it's possible to determine the symmetry of the resonant atom and in particular the coordination, the bonding, the orbital occupancy, and so on. In the EXAFS analysis, for example, the X-ray excite one electron which go into the continuum, and the wave function describing the electron in the material propagates through the material and is scattered back by the neighbor atom, and the scattered wave function which describe this interference pattern is proportional to the 2 times the distance of the path of the electron. And so from this kind of oscillation, the EXAFS oscillation, is possible to determine the interatomic distance of the neighbor atom, but also the coordination number of the atom. Here is one case, for example, for a nanocrystalline material, cadmium tellurite, which have a finite number of atoms. We can see that the EXAFS oscillation are very simple with respect the EXAFS oscillation in the bulk of cadmium tellurite, which present very strange interference oscillation. If we Fourier transform this EXAFS oscillation, we can see that the first peak corresponds to the first neighbor, the second peak corresponds to the second neighbor distance, and so on. In the case of nanocrystal, instead, we can see only one sharp peak associated to the first neighbor. This is due to the limited number of atoms present in the cluster. So this technique can be very useful for nanomaterial, which are reduced number of atoms, because in this case we cannot do Bragg diffraction, Thomson scattering diffraction, but for those system nanocrystal, but also for the amorphous material which don't present long-range order or eventually liquid solution, EXAFS is a very good tool to determine not only the interatomic distance between neighbors, but also the coordination number by integrating, for instance, the intensity of this peak. It's possible to use the polarization to study the magnetism, for instance, by measuring the linear dichroism, the circular dichroism. The linear dichroism is produced by a preferential absorption of one of two orthogonal photon polarization. The circular dichroism, they are produced by preferential absorption of two circular photon polarization. And this is in the case of magnetic material. We orient the material, the magnetic moment with a magnetic field, and we measure the ratio between circular left and circular right absorption coefficient. And by this method, using some sum rule, is possible to determine very important magnetization properties of material, like the orbital occupation, the spin moment, the orbital momentum, but also different kind of sophisticated symmetry, for example, for what we call non-reciprocal linear dichroism or Riemann-Eto-chiral dichroism. All these kind of properties which are derived by optical investigation can be used in the X-ray range. And of course, the absorption and emission spectroscopy receive a large advance with the improvement of the energy resolution, and can prove the different elementary excitation in complex material by measuring their energy, momentum, and polarization dependence. And of course, this is far from the limit of my talk. Just a few words about the optical properties of the X-rays, because I want to conclude with this. the existence of resonance scattering term due to the dispersion correction have some implication in the refractive index of the X-rays. The refractive index, the square of the refractive index, of course, is related to the frequency dependence of the electric constant, and we can see that the real part of the refraction index in X-rays, in X-ray range, is smaller than 1. And we call delta this factor, which depends from the Thomson scattering, the real part of the anomalous correction, and beta, which is associated to the dissipation term and is part of the imaginary part of the refraction index. For the X-ray, then, in the material, the refraction index is smaller than 1, and this is opposite to the visible light, we can see here, in which the index of refraction, the real part, is bigger than 1. And this, when we propagate an X-ray inside the material, the wave amplitude inside the material contain the refraction index in the amplitude. So the real part is associated to the phase shift, and the imaginary part associated to the beta in the refraction index is associated to the attenuation of this amplitude. If we want to take the intensity, of course, the intensity detected after the X-ray cross the material of a thickness Z is proportional to the linear absorption coefficient. And the fact that the refraction in the real part of refraction index of X-ray is smaller than 1 imply consequences in the case of the optic law. We know that the Snell law, for example, for the visible light, when a beam, a light beam, the visible light beam cross a surface with a material which have a refraction index smaller than 1, the emerging angle increase. In the case of X-rays, because the refraction index is smaller than 1 in the material, this angle alpha prime is smaller with respect to the incident angle in the air or in the vacuum. So to build optical lenses in the visible light, if we want to focus with the convergent lenses, in the case of X-ray, we need to build very strange lenses in which the air replaced by material, and the lenses is formed by hole, divergent hole in particular. I have to remark that the difference in the material with respect the air or the vacuum is very, very small. It's of the order of 10 to -5 in solid. Delta in the air for the X-rays 10 to -8. So these imply that X-rays optics is very cumbersome and very difficult to realize because the very low focusing power compared with the visible light. So for to build a convergent lenses in the bulk material, we need to build a lenses, a compound refractive lenses, which present many holes. And also with that, the focusing capability of the lens is very scarce. And this is one of the reasons why the beamline are very long, because it's difficult to focus the beam properly due to the fact that the real part of the refraction index is very, very small. We can build a mirror, for example, because below one critical angle, now we can have with X-ray the total reflection. This, the critical angle is called Brewster angle, and is equal to the square root of 2 times delta. And the critical angle, for example, for silicon, is of the order of milliradiant. So we need to build a mirror with a very, very high quality of the surface, avoiding slope error or roughness and so on. Here is an example of a silicon mirror which have a sagittal and tangential radius, silicon mirror with a toroidal shape, in which the distance from the source is 76 meters, the distance from the object 26 meters, and the glancing angle is 2.7 milliradiant. We can see that we need to build a mirror which have 27 centimeters for the sagittal focusing, but 27 kilometers for the tangential focusing. So you can imagine the technological difficulty to build such kind of surface of very high quality. Finally, I want to conclude some word about the X-ray monochromator. In order to select one given wavelength, we use perfect crystal, in particular perfect silicon crystal, and the perfect crystal works differently with respect any kind of mosaic, what we call mosaic crystal, because the kinematical diffraction theory don't hold anymore, and we need to use what we call dynamical diffraction theory or Darwin's theory. So the main difference with the Bragg, usual Bragg diffraction is that the intensity is no more a Lorentzian shape, but have a very strange flat top shape, in which we need to consider the dynamical diffraction problem. And the intensity, which is due to in general to the square of the structure factor for the standard Bragg intensity, now is replaced by just the structure factor. So we lost the intensity, but we gain in 100% of reflectivity in top of this curve, and in particular, this flat top can be modulated by increasing, can be reduced by choosing HKL index, Miller index in the diffraction. So, for example, a silicon 111 Bragg diffraction and 10 kilo-electron volt have a resolution, an energy resolution of about, I think, 1 electron volt, but choosing a very special asymmetric cutting and some shaped crystal is possible to reach very, very high resolution in the order of milli-electron volt. So the use of perfect crystal at the synchrotron give the synchrotron a huge possibility to improve the resolution, and so to study more in detail both the absorption spectroscopy method, but also the inelastic X-ray scattering method, and so on. And with that, I conclude. So I try to show the three main pillars of the X-ray scattering method. One pillar is the imaging technique, in which we can can extract spatial information, for example, by absorption contrast or by phase contrast. The scattering, which is very important for diffraction method, and the spectroscopy. Both these two methods aim to investigate the structural and electronic information in material, studying long-range order, short-range order, or local properties in amorphous material. And of course, the synchrotron science is very wide and apply in a many domains, all these scientific domain use this method to extract information by this high brilliant X-ray beam delivered at the large facility in the synchrotron and the free electron laser facilities. And with that, I thank you for your attention.